Hey guys, this is Jasmine from TechMuck Interview and welcome to another tutorial. Today we're going to talk about the carpooling problem, which is another interesting problem related to intervals. In this problem, you're given an integer called capacity and then an array of trips. And basically, each trip has three components. The first index is the number of passengers to pick up. The second index is the starting point in terms of kilometers. And finally, the last index is the endpoint for the trip. The question asks us to return true if it's possible to pick up and drop off all passengers for all given trips. Otherwise, return false. We have an example here. In this one, the capacity is 4 and we want to pick up 2 passengers from kilometer 1 to 5. And then we are going to pick up 3 more passengers from kilometer 3 to 7. You can quickly find out that from kilometer 5 to 7, we're going to have 5 passengers on board, which is more than our initial capacity, so we return false. In another example, we pick up 2 passengers from kilometer 1 to 5, and then another 3 passengers from kilometer 3 to 7. The maximum number of passengers for all trips from kilometer 5 to 7 is 5, which is equal to our given capacity of 5. So we return true. We're given some constraints as well. One of the more important constraints in this one is the length of our trips has to be less than or equal to 1,000. Another constraint is that the start point is less than the end point, which makes sense, and then the end point is smaller than 1,000. However, to make our solution kind of general, we disregard the 1,000 upper limit here. And at the end, I'll briefly talk about how this constraint can make a difference in terms of our solution. So without further ado, let's go to the next section, which is the algorithm section. So in this part, I have another example. In this one, the capacity is 12, and we should complete overall 5 trips. And we want to know if it's possible to make trips happen according to our current capacity. Okay, to better demonstrate this solution, I've created a timeline here. Let's go through each trip one by one. The first trip starts at 2 and ends at 3. So it's going to be this one right here with a capacity of 8 people. The second one starts from kilometer 1 to 3 with 4 people on board. The next one is going to be from kilometer 3 to 6 with only 1 passenger. We continue to the next trip. The next one is from kilometer 4 to 6 and is requiring 8 passengers. And finally, the last one is going to be from kilometer 4 to 8 with 4 people on the board. Okay, so let's find out the number of passengers in each of these time intervals. For the first one, the number of people from 0 to 1 would be 0. And from 1 to 2, the number would be 4. The number of passengers from 2 to 3 would be 12, as you can see. And passengers from 3 to 4 would be 1 person. From 4 to 5, it would be 1 plus 8 plus 4, which is 13. From 5 to 6, it'd be 13 as well. From 6 to 7, it would be 4. From 7 to 8, it would be 4 as well. Now, as you can see, there's an interval between 4 to 6 that exceeds our current capacity, which is 12. And the number of passengers here in this interval is 13. So we got to return false. It's not possible to complete all the given trips with a capacity of 12. Usually when we work with time interval problems, we need to somehow sort the intervals or insert the intervals in a sorted order. You might think of many data structures to give you this ability, but you need to find the right data structure depending on the problem you're solving. Here, one of the most important things to do is to be able to insert intervals efficiently in the data structure. One of the efficient and simple implementation of this method is binary search tree. However, in certain cases, like in the worst case scenarios, for example, if all intervals are given in already sorted order, the insert time complexity in the binary search tree would be O of n. We might think of a better and more efficient data structure called red-black tree, which is a self-balancing tree, and the corresponding implementation in Java is called tree map. It probably has other implementation in other languages, but in terms of this problem, I'm going to solve this one with the tree map, which is, like I said, a Java implementation of red-black tree and guarantees time complexity of log n in terms of insertion in a sorted manner. Okay, for now, let's consider that we found a data structure to give us the ability to insert each time interval in a sorted order. Now, having that data structure, let's see how we can solve this problem. Let's come back to the original state. When we added all the intervals in a sorted order. For this specific problem, on each time interval, I'm adding the number of new passengers when they get in the car and then deduct that number when they leave the car. In this example, at the very beginning, at time 1, we pick up 4 passengers, so I add 4 here. And then we drop them at kilometer 3, so I deduct the number by 4 here. At kilometer 2, we add 8 people, so I just add 8. And then here, we're going to remove those 8 passengers, and then I deduct the number by 8. This time, the total is going to be minus 12. Here we add 1 person, so it's going to be minus 11. And then at the end, we deducted 1 person, so this one would be minus 1 for the next interval. We started at kilometer 4 for 8 people, so we add 8, and then we finished our trip at time 6, so we deducted this whole thing by 8. And the final result is going to be minus 9. And for the last interval, we added 4 passengers, so this time is going to be 12. And then we remove those passengers here, and the final result is going to be minus 4. Okay, so I cleaned our time trip a little. It's more visible, and you can read it better. These numbers are basically changes in terms of passenger occupancy. Here we have plus 4 changes in our occupancy, and then plus 8. And here we have minus 11 passengers changes to our onboard people. To find out our current occupied seats, we have to add all these numbers together. Here we have plus 4 changes in terms of our occupied seats, and then here plus 8. And when we add them together, we end up with overall 12 changes in our occupancy at this moment. It's better to write it down like this. Here, the changes in our occupancy is 12, and the number of changes is minus 11. So the sum of changes in our occupancy would be 1. And then here, the number of changes in our occupancy is 12, so the overall changes in our occupancy would be 12 plus 1, which is 13. And then the changes in our occupancy is minus 9. So the overall changes in our occupancy would be 4. Here, the overall changes in our occupancy is 0. And then as you can see in one scenario, the overall change in our occupancy becomes 13, which exceeds the capacity that we were allowed to have. So we conclude that we're not able to complete these trips considering our overall capacity. Now, let's go to the next section and talk about how to write the code for this algorithm. Okay, so to implement the solution, first we add the tree map that we talked about earlier to store our intervals or trips. Note that here I didn't add the extra check for the edge cases, like if the capacity is 0 or when we don't have any trips, because our constraints already cover those cases. But in the real interview, you have to clarify the constraints first. And if the constraints allow for 0 capacity, you need to check for those edge cases at the very beginning. Now, we look through all the trips that we have. Here we have the number of passengers for each trip, and here I added from. And then the next one is to, or basically to this destination. Now I'm going to try to add those trips into our time interval map. I added from. I used get or default because in the case that there is no entry in our map, our default value would be 0. And then I add the passenger count. Let's do the similar things for 2. However, in this case, we deduct the value of passenger counts. As I've added all of our trips into the tree map, it's time to calculate the change in our occupancy and check if the occupancy change, or in other words, use capacity change, exceeds the allowed capacity that we have. I add the variable called used capacity. At the very beginning, its value is 0, and we traverse into our interval map. If you remember from the previous section, we added all the changes in our use capacity to find out our final use capacity here. Now it's a good time to check if our use capacity exceeds our allowed capacity or not. And if this is the case, we gotta return false immediately, and we don't check over the rest of the map for efficiency. Then at the end, return true if all the use capacity changes are in the permitted range, meaning that they're less than or equal to the allowed capacity. To calculate the time complexity, we have 2 for loops here. And in the first loop, we traverse over all the trips. So it's going to be O of n for the first loop. And then there are 2 insertions in the map. Because it's a tree map, it's guaranteed log of n time complexity for the insertions, and the overall complexity for this for loop would be O of n log n. And the next for loop is just a simple traversal to all the values in the map. So its time complexity is going to be O of n, and the overall time complexity for this solution would be O of n log n. And because we have a map that stores our intervals, the space complexity also is O of n. Now, is there any other way to improve the time complexity? The answer really depends on the constraints. If you look at the constraints, we see that our trip length is between 1 and 1,000. Considering that constraint, do we have a better replacement for the tree map here? I'll leave that improvement to you as an exercise to optimize the solution to reach O of n as our new time complexity. The solution that I provided here is a more generalized one, where the upper limit for the number of trips can be very huge. Okay, so let's quickly run this code to make sure that everything's okay. All right, it passes the sample test. Now I submit my code to ensure everything works. Here we go. Thank you very much for watching this video. If you like this video, don't forget to subscribe to our channel for more tutorials, and I hope to see you in the next video as well.